Today I am going to start a new topic, that is vector calculus. So first of all, let me talk about the derivative of a function. And the students who really want to appreciate the calculus, I will suggest them to go through the Janus paradox. And it's a very interesting, and you will really appreciate Janus paradox. That's a very beautiful story behind it, right? So let us start with the derivative of a function. So suppose there is a function just like this, and say it's a function and it is changing in this way with x-axis. Say it is x-axis and it is y is equal to f of x. So at a particular value of x, the value of the function will be f of x. Let us call this as f of x. And when there is incremental change in x, means x plus delta x, then what will happen? This is the value of the function, and this is f of x plus delta x. So derivative means how the function is changing with respect to change in the other variable. So that means the derivative of f of x with respect to x, it is basically the change in the value of function. So this is the change in the value of function. This is the final value and this is the initial value. So final minus initial with respect to change in value of x. This is the final and this is initial value, right? And if limit delta x means there is a very small infinite assembly, very small change in x, right? Then we call this as the derivative. So it is limit delta x approaches to 0, f of x plus delta x minus f of x divided by delta x. So this is the definition of delta x. Right? So similarly, as I talked about the derivative of a function, I will talk about the derivative of a vector quantity, right? So now there is a vector quantity. Say initially a particle is located at the position r. Now after some time the particle will be here, right? So particle will be here. Say the position vector changes from r to r plus delta r, and the position vector r at time t, and after some time, means t plus delta t time, its position will be r plus delta r. So therefore average rate of change of position with respect to time is given as, it is r plus delta r minus r, means it's the change in the position vector with time, and this is the change in time. So this t will cancel out with it, this r with it, so it can be written as curly r by curly t, sorry, delta r over delta t, or sometimes people call it as curly, but curly is basically this and this is delta, right? And it's a small delta. So as we saw capital and small letters, so it is the small delta. This is delta and it's a small delta and it's a capital delta. So in some books you will get either this way or this way, so it's not a big deal. So both are identical. So now if delta t means time approaches to 0, then that means what is the position in the next instant? So otherwise I can say that this is the instantaneous velocity. So that means if I put limit the delta t approaches to 0 and curly r delta r over delta t, if I try to find it out, then it is basically dr over dt, and we call it as instantaneous velocity. So that's why we call velocity as a dr over dt. All of you are familiar with it, but I have incorporated the idea of derivative here. Also, if r vector is given in terms of its components, means r vector is xi cap, yj cap and zk cap, then this velocity, it can be written as dr over dt, or it is dx upon dt I cap, dy over dt j cap and dz over dt k cap, or simply we call it as vxi cap, vyj cap and vz k cap. So therefore vx is equal to dx upon dt, vy is equal to dy upon dt and vz is equal to dz upon dt, right? And in the similar fashion, we can write down the value of the acceleration, because acceleration is basically derivative of velocity with respect to time. Or I can write down it as velocity is basically dr upon dt, so it can be written like this. So it is second order derivative of position with respect to time, or the position vector. And in terms of its Cartesian components, it can be written as d square x over dt square I cap, d square y over dt square j cap and d square z over dt square k cap. So this is a way we can look at it. So this is the acceleration, so it can be written as axi cap, ayj cap and az k cap. Another example is the force, and force is basically mass into acceleration, but acceleration can be written as second order derivative of position. So therefore it is md square r over dt, right? Now this is a brief idea that how do we calculate the derivative of a vector with respect to time. Similarly, we can also find out the derivative with respect to other parameter also. Now let us talk about a new concept, that is the differentiation of a scalar product of two vectors. Differentiation of scalar product of two vectors. Let me talk it about here. So let us choose that R is a vector and it can be represented dot product of two vectors. So let us assume that at time t, the position vector is like, the vector is written as a dot b, but as time changes from t to delta t, then at this time this r changes r plus delta r, or it can be written as a plus delta b, a plus delta a and b plus delta b. It's like this. So we have to take their dot product. So now this r plus delta r, it can be written like this. It is a plus delta a, it is b plus delta b, so it is a dot b, this multiplied with it, now this multiplied with it, so it is a delta b. Now this delta is multiplied with b and then it with delta b, so it is delta a multiplied with b plus delta a multiplied with delta b. Since delta is delta b are very small, that's why this quantity can be neglected, right? So if we neglect these quantities, then it can be written like this, and it is r. right? So it is A delta B plus delta A, and sorry, it's delta A dot P. So that means R plus delta R is equal to this. So this R will cancel out with it. So therefore this delta R can be written as A dot delta B plus delta A dot B. Now applying means dividing both sides by delta T and putting limit delta T approaches to 0. So it can be written as limit delta T approaches to 0, delta R over delta T, sorry, oh, it's not A, but A will remain as it is, but yeah, A delta B over delta T plus delta A over delta T into B. So it is dr over dt. It can be written as A dot dv over dt plus dA over dt dot p, right? So this is the expression for it. So therefore in nutshell I can write it down as that derivative of A dot B with respect to time, it can be written as first vector as it is and derivative of second vector with respect to time plus first vector, sorry, derivative of first vector with respect to time and second vector will remain as it is, right? Now let us talk about the derivative of a vector product or the derivative of a vector product, right? Now the derivative of a vector product, derivative of a vector product. So let us consider R is equal to A cross B. So it's at time t, and at time t plus delta t I can write it down as that R plus delta R is equal to A plus delta A cross B plus delta B, and let us try to simplify it. So it is A cross A cross B plus delta B plus delta A cross B plus delta B, right? So it is A cross B plus, here the order play a very important role. So it is A cross delta B plus delta A cross B plus delta A cross delta B. Now these two quantities are very small, so can be neglected. So now this is basically R. So it can be written as R, or here R plus delta R is equal to R plus A cross delta B plus delta A cross B. This R will cancel out with it. So therefore delta R can be written as A cross delta B plus delta A cross B. So now let us try to find out delta R over delta T, where limit delta T approaches to 0. So it can be written as dr upon dt. So as we did in the earlier case, it can be written as A cross dB over dt plus dA over dt cross B. Here order of vector must be strictly maintained, so we have to keep this in mind. So let me write down that point here. Order of vectors must be strictly maintained. strictly maintain time. So that's it. And similarly we can write down other formula. So first of all, let me write down for the scalar triple product. So it is d upon dt of a dot b cross c. So here we have to take the derivative of first. So it is d upon dt dot, and second and third vector will remain as it is. Now first vector as it is, now dot is here, so dot will be here, and derivative of second vector dv over dt, and third vector will remain with the cross product, right? We have to keep these things in mind, plus a dot, similarly b as it is, cross dc over dt, right? So this is for the formula for the derivative scalar triple product. And similarly we can write down the formula for the vector triple product. So here it is a quantity d upon dt of a cross b cross c. So it can be written as derivative of first, and second will remain and third will remain as it is, plus a cross dv upon dt cross c, plus a cross b cross dc over dt. So these are some very important formula which we have to keep in mind. So here in this lecture I talked about a brief review of that, how to find out the derivative of some vector quantities with respect to some scalar, and that is time here. So that's all for this lecture.